Hey everybody, this is Brent Jones, Industry Manager for Land Administration at Esri, and thanks for coming to today's meetup. It's going to be a good one. We've got Catherine Smythe and Alberto Nieto, and uh, as you all probably know, these are a little bit less formal than our regular webinars, so type questions in the chat window, and I'll be pasting links in there as well. And over to you, Catherine.
Thanks, Brent. Hi, everyone. Today we have Alberto Nieto, my colleague here on the Solution Engineer team supporting national government. I'm really looking forward to this presentation today. I think Alberto has a lot of great insight into spatial statistics. Please, like Brent said, as we move along, type your questions in and I'll be on the line to answer them. And I'll hand it over to you, Alberto. At the end, we'll answer a few questions live if we have time. But otherwise, enjoy. Thanks.
Great. Thank you so much, Catherine, and thank you everyone for joining us today. Again, my name is Alberto Nieto. I am a solution engineer in our national government team based out of the Washington, D.C. office. And today we're going to talk about spatial statistics, which is a topic that is dear to my heart. And I hope that by the end of this presentation, you'll see a lot of the value of these concepts. Some of what we'll cover today will be pretty broad. Some of it will be a bit more specific, especially towards the end. So the way this presentation is tailored is it's intended to give you something useful, whether you have a lot of experience with statistics, with spatial statistics, with GIS, or even if you're brand new to the concepts. I think there will be a few things that you can take home with you at the end. So before we get into it, really, what are spatial statistics? There's this cold, hard dictionary definition that talks about spatial statistics being a set of exploratory techniques that indeed describe and model spatial distributions, processes, patterns, and relationships. But this is a little bit cold and maybe doesn't really do the concept justice, because in a lot of our views, spatial statistics are really working with concepts that we inherently perceive in the world, like proximity, orientation, connectivity, things that make us proud to be geographers and to use that information when we do analysis. And really, they're an extension of what our brains do naturally when we perceive the world. Whenever we see a map, the first thing that we are drawn to do is to infer patterns on a map. On any image that you're portraying the world with, you will see clusters of points, you will see patterns, and your brain is this tremendous statistical machine that is just tremendous at finding information from the world, but very often it can sometimes find patterns even when they're not actually there, even when they're not explicit or when they're not things that you should actually be paying attention to. So in many ways, spatial statistics is a way to almost protect yourself from that bias that you may bring to bear whenever you look at a map, whenever you do analysis. And I think it deals with a concept that most of us are coming across more and more often these days, this distinction between having data or having information. And most organizations, I think, will recognize the problems when you're data rich but information poor, right? If you have a spreadsheet of several 100,000 records, perhaps portraying the salaries of each employee in a company, if you're a decision maker, you're not really going to be able to do much with a table with hundreds of thousands of records alone. You're going to ask analysts and people that work with data to make it into information so that you can do something useful with it. You may ask people to do more, such as compute averages, the mins, the maxes, the statistics that you care about. But for some reason, when we go into maps, as soon as you load information or data into a map, a lot of people think that we've made the jump into information right away. And that's not always the case. Very often, people are satisfied with taking a spreadsheet of people's addresses or locations and simply dragging and dropping it into a map and seeing points on this map and calling it a day. But I would like to propose that that very much still is data. You're not really getting to in most cases, you're not getting to the information that a decision maker really yearns for when they try to make an informed decision. So just like when you look at a spreadsheet and you take some action to derive information from it, you may, again, compute the average, you may look at the distribution of some field, etc. You can do the same with spatial data, with maps. You can compute means, centers. You can look at interpretations of geography and how these concepts come to bear to make data useful for you. So a lot of what we'll cover today goes with that concept. We'll start with basic items related to means and medians and summarizing spatial distributions. These are simple but very elegant methods that, even though they're simple, very often can go a very long way in helping you understand something interesting about your data. And then we do get into some more complex methods related to machine learning, specifically with clustering, which is a very useful technique when you're exploring your data. So let's get into means and medians. What I'd like to do is go through a few different capabilities and tools. First, from the perspective of the concepts and how they work, and then I'll show a few demonstrations that show how the tool is actually working in action. The first tool is one of the simplest. It's called central feature, and we identify the most centrally located feature in a data set. So perhaps you have a data set with points in your ArcGIS Pro project, and you'd simply like to find the most centrally located point among a distribution of points. The way the tool works is that it will take all of your input data, plot it on your X and Y axis, and then compute the distance from any given point to all the other locations in your data. Then go to the next one, compute those, next one, and compute those. And then when you compare, essentially when you stack those distances together, the one with the shortest total distance is your central feature. So a fairly simple tool, but it's actually quite powerful when you try to think about giving additional information to the features that you do have. In a similar way, if that's the central feature, we can also calculate the mean center of a set of features. And in this case, the big difference is that you're not identifying one of your points as the central feature, but you're actually creating a new point that happens to be the mean center of your population. And you can actually calculate this manually fairly simply. What we'll do is we'll take the points, their latitudes and longitudes, or XY coordinates, and then compute the average of both the latitude and the longitude. And that will become the mean center of your population. One more tool that I'd like to briefly go through is median center, which is very similar to mean center, but instead of taking the average, we will take a look at the median and create the new feature that represents that new coordinate. So very briefly, in statistics, you may have come across this concept early on in your classes or in your work. But in spatial statistics, the same concepts of mean versus median come true, right? If you have an outlier in your distribution of points, that outlier may affect the mean drastically, but it would not affect the median as drastically. So the median stays put, and signified by this purple cross, but the mean center has been affected by the presence of that outlier in the top left corner or top right corner of the map. So different analyses, questions, and different purposes would use one tool or the other. There's also a way to actually calculate the linear directional mean of your features, and this really pertains to a set of lines. So instead of points, if you have a sequence of linear features, perhaps the trajectories of hurricane paths or tornado paths, and you're trying to determine the average directional, the linear directional mean, the tool essentially will calculate this, and it'll take the average angle of all the linear features you have and use that to digitize that new linear feature. Finally, there's one last tool that I'd briefly like to cover, and this one is called directional distribution. Many of us simply refer to it as ellipses. And this one is likely one of the most useful ones because it sort of encompasses a lot of all the other tools that I briefly covered in one tool. It will calculate your mean center, and it will also determine a sense of how dispersed the other points are around that mean center, and also calculate directional trends. So the way the tool works is it'll start with this mean center of your population, and then it'll determine the standard distance on both the x-axis and the y-axis, which will let it create this ellipse. So in one run of a tool, you get a lot of information about the distribution of your data. You get that mean center and also how dispersed the features are around that mean center. So with all that, let's actually jump into a demonstration and see how this would work in action. So we're going to start with a few basic scenarios. And again, these are basic tools, but in my opinion, they're very elegant because very often the first thing you want to do after you create a map of points is start to get some information out of that map of points, and perhaps the mean center, the central feature, can help. In this case, we're going to put on the hat of being a fire station manager. So these are fire stations near Arlington, Texas. And the idea here is that we want to identify if you're the chief of this department, of this entire region, and you want to find a station where you'd like to position your office so that you're most centrally located and are able to visit the other fire stations reliably, which feature would you use? So all of these tools that I briefly covered can be found in our spatial statistics tools toolbar or toolbox, and under the sub toolbox called measuring geographic distributions. The first one that we'll do is central feature. You can simply drag and drop your input points into the input feature class, give it an output feature class name, and then run the tool. So one of these stations happens to be the most centrally located. You can do this visually, but it makes sense to have the tool calculate that for you. And this station might be a good candidate for that fire station chief that wants to position themselves right in the center of this district. If we go over to mean center, this example is going to be a little bit different. Instead of having points, the tool can also work with polygons as an input and use a field or some value for each polygon to determine the mean center of your data. So what we're looking at here is the distribution of population in California over the past several decades. So this is 2010. Darker means higher population counts. As we go back in time to the 2000s, we see different changes in population distributions. And what we'd like to do is use mean center to actually determine what the mean center of population for California is over the entire past century. So what we're going to do is we can merge all of these features together and pass that as a single input feature class to the tool. And there's a few parameters here that you may have noticed when I opened up the tool earlier. The first one is weight field, and what it allows you to do is pass a field that it will use when it calculates the mean center. So what we do want to do is tell the tool to use the population as the weight for calculating those mean centers. Next, there's a case field parameter, and case fields are pretty powerful because it lets you run the tool for as many times as there are unique values in a field. For example, if we open up this datasets attribute table, you will see that there's a field called population year, and this corresponds to the decade of the data. It goes all the way back to the 1900s. So we can use that as our case field, which actually saves a lot of time. You wouldn't have to run each input individually. We're going to run the tool. And what it will do is it'll calculate several mean centers, kind of telling the story of population distribution across the century for California. So here's the different mean centers, and I'm going to label them so that we can take a look at what each point represents. Let's change this very briefly to Python. Instead of ID, I want to display the population year. Go ahead and apply that, and we have the different dates. You can also go ahead and do some trimming here on the label so that we only represent the, there we go, the last 4 characters. There we go, I had wrong syntax there. Okay, and what we're telling here is that in the beginning of the century, in the 1900s, a lot of what drew the population to California was the gold rush. Most people lived in this region of the state towards the center, closer to San Francisco. But then going later in time towards the 1930s, 1940s, 1950s, then Hollywood started becoming a drawing force to California until you have the mean center of population more recently in 2000 and 2010, stabilizing right around the area of Bakersfield. So mean center, quite a powerful tool, even though it's such a basic concept, you can pass different information to it, such as polygons with values. One more quick example is median center. Median center, in this case, is working with a data set of library patron locations. So let's say that now you're wearing the hat of a librarian. And these are 3 library districts where you can place a mobile book drop-off cards. What you'd like to do is place these mobile book drop-off cards in the most appropriate location for each district. But what's interesting about these 3 districts are that the green district has a pretty odd shape where you have several locational outliers. And in this case, a median center might be more appropriate than the mean center. So what we'll briefly do is pass our input patron locations. And then for our case field, we're going to tell it to use the district ID so that it calculates 3 possible mobile book drop-off locations. And then run the tool. So we should get 3 median centers, and those could be good candidate locations if you're starting to look at places where you could position this mobile book drop-off card, particularly when you have data with really interesting shapes and distributions like this southern district. That might be when median might be more appropriate. But of course, you can see the tools don't take that long to run, so if you're curious about comparing this to mean center, just run both. Finally, I do want to show you the ellipses version of the tool. So I mentioned that ellipses does a lot in one sweep. And very often what I find myself doing when we get a new data set of point locations is just pass it through ellipses and try to get the mean center and the distribution of those points around that mean center. In this case, what the scenario shows is something called Ushahidi data. Ushahidi pertains to events or to incidents, particularly around elections. Right now, we're looking at incidents in Libya. And if we create a quick chart and portray the dates of each incident, this takes place around a 9-week span from, let's see, this is March 1st through April 25th or 26th rather. So a 9-week period. And what I'd like to do is we can run ellipses for this once, but I want to see what the dispersion of these events and how it changes over each week of the data set. So we'll go to that tool, standard deviational ellipses, pass our input data. And then over here, you can determine the ellipse size. So it will determine the dispersion around 1 standard deviation from the mean center or 2 or 3. We'll keep it at 1. And then we will pass the week of the event as our case field. So the tool will run for however many weeks of data we have. And if some events were more important than others, we could specify that in the weight field. But for now, we just care about the fact that each incident occurred. So we get these ellipses, which might be a little tough to interpret by default because there's so many. But what we can do is we can use the properties of that layer and create something called a range slider. The range slider lets us select one of the attributes here, and it creates this GUI component that lets you determine what week's worth of distribution you're looking at. So this is week 1, week 2, week 3, week 4, week 5, week 6, week 7, week 8, week 9. And you see that as the time period goes on, the incidents get a little bit more clustered around the mean center of that particular time period. So that can be an interesting way to summarize your data if you really are just trying to explore some new data set that you have. Okay, let's go back to our PowerPoint. And again, those are basic and pretty straightforward methods. I think it's not you could calculate all of that manually, but it's pretty nice to have tools that do that easily for you. And as you get into exploring your data and particularly getting it ready for more complex methods like the ones that we're about to cover here, having a good fundamental understanding of those things like your mean center and the dispersion can be really, really useful before you get more complex. So now let's get into machine learning and some of the methods that are newer to ArcGIS. The first one that we're going to cover is called density-based clustering. And this tool is really about determining location-based clusters based on the location of each feature. The idea here is that you may have a distribution that looks like this, and you may inherently see perhaps 5 clusters. Some people may see 6 clusters. We want the tool to be able to arbitrarily tell us how many clusters it can identify in your input data. Knowing that you have clusters can help you when you're trying to organize a data set or identify patterns in incident data. And the way this tool works is it's actually 3 tools wrapped up in one. It has 3 methods that we can invoke. The first one is called dbScan, and it's the simplest method. The second one is called HDBScan, and it really works with machine learning concepts to determine what a cluster means. And the final one is called optics, and that one lets you tune the definition of a cluster the most. So let's go with dbScan first. This one is the most manual. This works well if you already know what the definition of a cluster is. First of all, it starts with a defined distance and a set amount of features per cluster. So for instance, if we specify that we need 5 features per cluster, no less, the tool will first determine the chord distance for each point to find those 5 features. And then it will compare that to your specified search distance. If that chord distance to find those 5 features is less than the specified search distance, you have a cluster. If, however, to find those 5 features, your chord distance is much greater than the search distance that you provided, then you have what we label as noise. And the second method works if you don't really know what the definition of a cluster is. So dbScan, the previous method, worked well if you really know, if you have subject matter expertise that perhaps knows exactly what you're looking for with clusters. But in many cases, we don't know what a cluster really is. So HDBScan is self-adjusting, meaning that it will change those search distances depending on the distribution of your data. It can be really appropriate when you're comparing clusters in rural areas versus urban areas, as an example. And finally, we have something called optics, the third method. Optics is really appropriate for letting you fine-tune exactly what your cluster outputs are. And optics works with the concept of a reachability chart. What we'll do is we'll calculate the distances from one point to the next and plot those on a chart by feature order, seeing the reachability distances. If you notice some of those lines that really take a long gap to find the next point in the feature order, look like peaks in this reachability chart. And those peaks may emerge above the rest. And those are good candidate starting locations for either a new cluster or for noise. So by this default run of the tool, it would find these different peaks, and those peaks would establish whether you have the start of a new cluster, essentially these valleys that compose the cluster with low reachability distances, or you may have a noise point that is on its own. Now, on the far right of the screen, that blue cluster, you may say that there's a smaller peak there that nonetheless is important for you to separate. So you can tweak using a reachability parameter to tell the tool to be more sensitive to those peaks. So it could actually split those two, that single cluster into two discrete clusters. So in summary, we have these 3 methods for clustering using just location. dbScan, which is very fast. It uses the fixed search distance and the clusters of similar densities concept. It works well if you really know what a cluster is. If you're a transportation safety engineer and you know that you would go try to address an intersection if it has 10 fatal crashes within 500 yards, for example. Then you would use dbScan to find those locations in your data. However, if you're a crime analyst and you care about different densities in downtown LA versus a suburb of LA, and you want to run a single analysis that captures those different densities, you would likely use HDBScan, which is really using different ways to define what density means in your data. It's data driven, but it requires much less input because it's letting the data speak for itself. And finally, you have optics, which can really let you fine tune and sort of defend why you're finding these clusters with that reachability chart. Let's take a look at a quick demonstration to show you how these tools work. So in this case, we're going to take a look at traffic data in Los Angeles. This is a data set of Waze incident points. The data set spans about 98,000 records. Really, when you look at a map of points like this, it almost just follows the road outlines. It's basically a map of streets in LA because there's so many traffic incidents in LA. So what we'd like to do is really start to break apart this data set and organize it a little bit. If you're trying to identify places where you can remediate in Los Angeles, very likely you're not going to simply provide a map like this to a decision maker. So what you would likely, one of the options you would do is open up spatial statistics tools, open up mapping clusters, and go to density-based clustering. You can pass our input Waze points. And here's where you select which method you would like to use. We'll start with dbScan. Again, it lets you specify how many features per cluster. We're going to specify 100, saying that 100 incidents is enough. And you can then specify your search distance. The search distance, by the way, is optional. You can let the tool identify a smart default for a search distance, which is appropriate in this case. And another quick tip while this tool runs, if you're starting to use some of these tools, I highly recommend that you select this question mark option. If you actually click it, it takes you to the tool documentation. And that tool documentation can really help you understand how these tools work and maybe even include it with your analysis if you're trying to defend an output. Okay, so this is the output of dbScan for this Waze data. And what it found is these clusters throughout the city that correspond mainly with highway intersections, which makes a lot of sense in terms of incidents that cause heavy traffic. However, because dbScan uses the single definition of a cluster, it really can't deal with the different densities between downtown Los Angeles and the suburbs and Anaheim and other areas. So the single definition of a cluster worked well for these regions over here, but as soon as we go into downtown Los Angeles, downtown LA, it's just this massive single cluster over here and over here that becomes a bit tougher to deal with. So one thing you could do is subset your data into downtown and non-downtown, but better yet, what you could do is change this to HDBScan and let the tool define these different densities for the more dense regions of your study area versus the non-dense regions. I've already run that for HDBScan, and this is the output that it would get. You do get those nice clusters in the intersections outside of LA or outside of downtown LA. And then when you get into downtown LA, you get much more definition into the different regions within the more dense parts of your study area. Finally, with optics, if we change this to optics, you have this new parameter called cluster sensitivity, and this is what lets you define how sensitive the tool is to those peaks in that reachability chart. And if we turn that output on, I feel like this is the output that I'm much more comfortable with. And part of the reason is because it provides that reachability chart with its output. So if I collapse this and take a look at the distribution that we find here, we have our map on the top with the different clusters, but we also have the reason why those clusters were selected with this chart on the bottom. So if we zoom into one part of our chart here, we can make a selection and we see this valley over here with all of these points, these Waze incidents that were found, where the reachability distance between each point was quite low as soon as you pass that peak valley or that peak over here. that corresponds to that cluster over here. If you wanted to keep tuning the model, you could raise the sensitivity and let some of these peaks emerge and have different clusters within that region. But this is quite useful when you're trying to simply explore your data and organize it. The fact that one incident belongs to a cluster or doesn't belong to a cluster can be really important when you're trying to prepare data for more analysis. Finally, one more capability with density-based clustering that I like to highlight is the colors of the tool are really important. And the colors are really determined by something called the four-color theorem. And so ArcGIS is not the only software package that will run density-based clustering or dbScan. You can do that in Python, you can do that in R. However, in those packages, when you get these clusters, when you're trying to visualize that information, very often the default output will be this color ramp with several dozens of colors. And that can make it really difficult to interpret the information that you're getting. But with this tool, it determines the right color using that four-color theorem, which was, I think it was derived from atlases that determined that you really only need 4 colors to portray all the countries in the world, provided that there's a rule that bordering countries don't have the same color. So it makes it a lot simpler to interpret these different clusters because they're guaranteed to have distinctive colors, but you don't have so many colors that the output becomes a little difficult to parse. So there's a lot of interesting and powerful capabilities packed into these tools that go a little bit deeper in the weeds in terms of how the symbology is produced, how you can view the data, and the smart defaults that they have.
Are there any questions on this demo? If there are, just type them in the chat window. It was pretty good, Alberto. Thanks.
Great. So that is clustering with regards to location. The next demonstration is clustering with regards to data, to attributes, not necessarily location. So very often we may need to cluster our records in our data based on how similar they are in value. And the tool that we have ready to do that is called multivariate clustering. One example that it helps address is this idea of comparing different maps to each other. Perhaps you're trying to identify areas where you can remediate uninsured populations. Maybe you have areas with really high percentages of uninsured populations. And you have these 4 different variables that you're comparing. On the top left, you have percent eligible that is uninsured. Then you have different breakouts with uninsured that have no high school, uninsured that are Latino, etc. If you're trying to find this area to remediate and you're comparing across these 4 maps, it becomes pretty difficult to really keep track of 4 sets of information at once. So clustering there makes a lot of sense if you're using these 4 attributes as a clustering input. And it uses an algorithm called k-means. K-means looks at data space and you tell it how many clusters you need to create, and it'll find the right ways to cluster your data using that information. So for example, we have a distribution of data, not in space, but in attributes that looks like this. And we tell that tool that we want to create 2 distinct groups to remediate. Very easily, you could see just visually by plotting the data on a chart that there are these 2 distinct groups. They're very similar within a group and very dissimilar without a group. If you wanted to pass it, let's say you had 3 groups that are going to remediate. Maybe the 3rd cluster would be a distinction between that first green cluster, right? But what if you have 4? Then we'll try to split the data up logically where it makes the most sense. So you really need to know how many groups typically you want to split your data up by. An example of what the tool output would look like is this map. So now we're looking at both a map, and you really need this box plot to help explain the outputs and the distinction between each cluster. If you take those 4 variables as an input, it will find these distinctions between and when it groups these 4 variables. So the group in blue, in my view, is distinctive because it has lower values of percent uninsured, lower values of percent no high school, and about average values of percent Latino. Whereas the group in red really is distinctive because these are the areas with high percent Latino populations and higher percent uninsured and higher percent no high school. One more variant of that tool is the same concept, but adding in a constraint that everything has to be spatially contiguous, meaning that all the features have to touch each other if they're a part of a cluster. So if this example was, let's say that one requirement is that every cluster had to be contiguous, and you really couldn't have remediation happen if the zone had a hole in it, essentially. Then you would go to this tool, because what it does is it uses a minimum spanning tree to determine where the clusters make sense to split. So you may have this minimum spanning tree. It's not just location in this case, but it's location and data and attribute data. It will find the places where it makes the most logical sense to break apart this data using those two factors, that constraint. An example of where this is useful is if you have like a police department that is trying to identify zones for different precincts based on these criteria, like median income, high school dropout rate, unemployment, crime count. You wouldn't really want to have these zones be not contiguous, because you don't want a police patrol to have a zone where they go to one block group and they suddenly have to travel quite a bit to find the next block group in their zone. So let's take a look at a couple demonstrations that I think really show how this tool can assist. So in this case, we're working with a data set from the Robert Strauss International Institute. And in this case, we have administrative boundaries in Africa showing vulnerable metrics. This is population density index, really just showing one variable that may be related to vulnerability for different issues. But if we open up the attribute table, we see that there's all this other information, such as climate-related vulnerability. If there's climate-related flooding, how vulnerable would you be? The higher the index, the more vulnerable you are. There's also household resiliency indices. So how much access to care do households have, to medical care, to safety, etc. You also have new governance index. So how stable is the government in that region? And all of those can be taken together and assigned to a new overall vulnerability index. But the problem is that you're losing some of the information from these distinctive fields when you do that. So another approach that you can take is to actually go to multivariate clustering, pass your input features, and then use those analysis fields to create your clusters. So first we'll choose population density index, climate index, household resiliency index, and then the new government index. And then we'll tell the tool that we have 4 remediation groups. So we want 4 clusters. And let's go ahead and run the tool. So the output of this tool is this layer, but I recommend if you ever run this tool, you really need to open up the box plot right away to interpret what's happening with your analysis. So we have these 4 clusters, these 4 groups for all of the administrative regions here in Africa. To my mind, the first group that stands out is this yellow group, or almost orange. And that's identified by high climate index vulnerability. So these are regions really in the coast, right? In the far north, far south, Madagascar, that climate-related events would really become a vulnerability problem there. If you have a remediation group and experts in flooding or experts in climate-related problems, these are the zones that you would likely send that group to. The blue group is quite a bit different though. Its climate-related index problems are not as significant, they're about average, but the household resiliency index is the issue that makes that group really distinctive. So these are areas that, and also new government index, so these are areas a bit less stable, such as Somalia, etc. So the different remediation groups that would go there obviously would have different skill sets. And finally, this red one is characterized by a really high population density index. So these are the most populated regions of the continent. One additional example that I have here is spatially constrained multivariate clustering. So it's the same idea, but now we're making contiguity a need. And what we're looking at here is ecological data. So these are ecological marine units. These are points corresponding to ocean health. Each point represents a few different values, such as the temperature of the ocean, salinity, dissipated oxygen, nitrate, phosphate. And that can be useful information if you're trying to assess the state of the oceans throughout the world. So we can run a similar analysis, but in this case, we will run spatially constrained so that each region is contiguous. We'll pass our input ecological marine units, or EMUs, let the tool specify an output, and then use our input temperature, salinity, dissipated oxygen, nitrate, phosphate, silicate as our inputs. And then we'll tell the tool to create 7 clusters. So behind the scenes, if you're interested, the algorithm that it uses is called Skater, which is really powerful in different applications. But in our software, we make it available quite simply. The idea is to make the tools powerful but basic to use or simple to use. Anyone can really run Skater through that tool. So here's the output, and again, go ahead and open up your box plots to interpret why you got these clusters. You have these contiguous groups now. You don't have regions that are separate from each other. And the one group that stands out immediately to me by looking at the map and at the chart is this purple group. And that's characterized by really low salinity values and essentially finds the inland seas of the world, the Caspian Sea, the Black Sea, etc. You may also have other seas that are characterized by differences in temperature, such as this northern group, etc. So that could be one way to do that. I also have a brief example of the vulnerability piece where we were looking at Pakistan for the World Food Program. If they're trying to remediate and create regions where they're going to distribute food, and they're looking at different vulnerability indices. This is what it would look like if you just run multivariate clustering versus if you run it with the spatial constraints. So that can be important if the group that you send really needs a zone to find. So those are multivariate clustering and spatially constrained multivariate clustering. 2 tools that are pretty similar but can be useful for pretty different purposes. So finally, we're going to take a look at one very new tool. This is called Build Balance Zones. And it's somewhat similar to clustering, but it's actually the opposite. With clustering, very often what we're trying to do is find these groups of data that are very, very similar within each group. And outside of that group, they're very dissimilar. With Build Balance Zones, we're trying to find groups that are really similar to each other and are all balanced, hence the name. One example is if you're trying to create, for example, territories for cells or territories for evaluation, for example. You may want each zone to be representative of a group that's very similar to another so that no one gets an over or a much tougher task with their zone. The way the tool works is that it has these different criteria for creating zones. It could find an attribute target. So let's say that a zone for a salesperson cannot have more than 100,000 homes in that region. So that could be the attribute target. You could also tell the tool to have a specified number of zones and an attribute target, or just the number of zones. When it builds each zone, it can also consider additional constraints, such as the zones being equal area or as compact as possible. Or also you can tell it an attribute to consider. So for the sales territories, if you have a field that specifies how likely are people to purchase already, and you want that to be balanced across different sales territories, you can pass that as a field in the analysis. And the way the tool works is with a really fascinating concept called a genetic algorithm. So it sounds a little complex, but the way it works is that you have your input data and it will try to first establish a potential seed for each zone. So a seed is just one feature. And from that seed, we grow a zone. Then we go and create another seed outside of that zone and grow another zone. And then another seed, grow another zone, and so on. until we have our data set with its first generation of zones and seeds. Then we're going to determine how fit is this particular configuration of zones and seeds for the optimal answer, where everything is as balanced as possible. That'll give us a number, but that's likely not going to be the best solution. So what we'll do is we'll mutate those zones, we'll change the seed and grow different zones and compare and see which of the two configurations is more appropriate. One of those two is better. So what we'll do is we'll select those seeds that were better than the others, and those top 50% seeds move on to the next generation. And then the ones that were dropped go away. And then we'll take the remaining ones and mutate them a little, basically cross over and create different configurations of seeds. And those create new candidate zones for balancing. And so on, and so on, and so on, until we find essentially the optimal answer. And that optimal answer is also provided as a chart that you can take a look. This is very akin to machine learning training. When you're trying to find the optimal model, it essentially iterates over training data several times until it finds the lowest error, and additional iterations don't really yield a better output. In this case, it's similar. Each generation is an iteration, and we're trying to find that place where the tool plateaus and doesn't get any more balanced outputs. That's a little complex, but really what it means is that it lets you find this optimal answer. So let's see a demonstration. So the example I have here is actually, even though we're talking about genetic algorithms and machine learning, this example is actually meant to help a local high school marching band. So even a high school marching band can make use of machine learning. The idea here is that we have all of these homes distributed around this, this region. This is Northern Virginia. And we want to organize a campaign for the local high school marching band to reach out to each home and ask for donations. And we're going to have a set amount of volunteers that will help for this event. One way in which you can try to organize this event is to find these balance zones. So here's the tool. You specify your input features. In this case, it's going to be our homes. Your output features, what you're going to receive as an output. And then your zone creation method, you can consider, to start with, I would recommend that you actually just look at the number of zones to kind of become attuned to the tool. Let's say that you have about 30 volunteers that agree to come help ask for donations. So I'm going to enter that I want 30 zones. For spatial constraints, we're going to leave it by default, but essentially this is how the tool sees different homes and the distances between homes when it tries to balance. And then there's also advanced parameters that let you tune how the generations and the mutations occur. But we're just going to run it like this. So what you're going to get are these 50 regions in your neighborhoods. And these 50 regions could be appropriate for each volunteer to go canvas or to go ask for donations. So this is the output of the tool. You get these 50 or nearly 30 regions rather. You get this chart that gives you how many features are considered by zone. When we ran the tool, we also specified actually that we want the zones to be as compact as possible. So it's not simply going to balance by how many homes each volunteer is going to get, it's also going to balance by how compact the zones are. This zone up here, if I select this group, likely has fewer homes, but it also has compactness to consider. So that may be why it received fewer homes. However, there's a problem here with the default output. If you look at this complex, for example, people would go in, reach out to a few homes, and then have to come back out. So the tool also has a way to incorporate road networks into its input. If we go to something like this, let me turn off this layer. We have these road network segments that we can tell the tool to incorporate when it runs. And I've already done that. So the way you would do that is there's a parameter down here. So let's say build balance zones with roads. There we go. You can tell the tool to get spatial weights from a file, and that file can essentially incorporate the road network. And when it balances using that file, it looks quite a bit more appropriate. So let me show you what that looks like. It will create all of these zones. Once again, we have nearly 30 zones. And now there's quite a few different zones that have a lot more features or a lot fewer features. But the reason is because we're also telling homes or volunteers to be contiguous with consideration for the road network. So now this makes a lot more sense. Someone would go into this housing complex and finish the entire housing complex before they're done, not have to wait for someone else to come help with that region, and so on for the other people in the particular event. What I also like is that, let's say in the day of the event, things really change and you don't have 30 volunteers, but you actually just get like 22 people that showed up. If you suddenly had to create maps for the 22 people, you would simply change the target number of zones, change your output name, and run the tool and get your new zones. And then publish these maps and give them to each person and quickly adjust for the different dynamics of what actually happened in the real world. So once you get your output, you would get larger zones because now we have 22 people instead of 30 people. But once again, these would be balanced using all of those different criteria. One last point with this particular demonstration and this tool is that it uses, within machine learning, we're talking a lot about predictive analysis, right? Or clustering, where these are things that explain data. For example, clustering will tell you whether you have groups, etc. And prediction will tell you perhaps what things will be in the future or in an area that you don't know about. But this tool gets into something called optimization, which is really fascinating because it starts to tell you what you should do. It goes beyond prediction and tells you, here's the best answer given all the different factors. And I think that's really where analysis is at its peak, when it can really tie all of the data into a specific recommendation for some decision maker of this is the way you should do things. And optimization is really what this tool works with to do that. So that's a lot to cover today. We went from pretty basic methods to much more complex methods, but I hope that you were able to learn at least a little bit about spatial statistics and be curious about these problems and tools. I do have a few resources that I'd like to share with everyone in the call. First of all, there's the first website. It's called surl.com/spatialstats. That takes you to a web page with a lot of resources. So this is what it looks like. You can take a look at presentations and recordings that go a lot deeper in some cases. For instance, if you really care about data visualization and charting, this presentation gets into those concepts. Or if you care about regression and predictive analysis or clustering in space and time, I recommend that you take a look at some of these videos. Additionally, there's hands-on exercises. So if you actually want to try it out and learn how to do clustering analysis or regression for prediction, a lot of these concepts help there. And finally, there's learn.arcgis.com, and we have an entire team dedicated at Esri to create these learn lessons. They come packaged with data and with exercises that really help you go through the entire analysis workflow. One specific example that I think is particularly useful is if you enter machine learning here in the search part of lesson gallery, there's an example that talks about downscaling climate data with machine learning. This exercise is quite lengthy, but if you do want to learn about machine learning and how it can assist with GIS analysis or analysis in general, this exercise is quite extensive, but it really helps you prepare for that. Finally, I do want to plug in an upcoming event that we're very excited about called the Esri Spatial Data Science MOOC. A MOOC is very much it's a course that is actually about to start next week. If we go to that webpage, I can provide you some details. So this is about 6 weeks long. Each week you could expect to spend about 2 to 3 hours of study and exercising, but you can take it at your own pace. It's free. You don't have to pay anything, and it comes with trial licenses that you can actually use. And it starts on February 26th, next week. We're about to start with the first lesson. I highly recommend that if you're interested in these topics and looking to learn about the latest and greatest, this MOOC is really tailored to help you go through the whole workflow. And with that, I'd like to thank everyone for your time and your participation in this webinar. It would be great to meet you at some point, but for now, I will have to say thank you and ask if anyone has any questions.
Thank you so much, Alberto. That was great. For those of you on the call, I hope that you found this to be enlightening. Whenever I listen to Alberto speak about spatial statistics, I start drawing these lines between what the examples he's showing say and how I can use that for my work in property valuation. And I always come away with a lot of inspiration. So I hope that you had a similar experience. I'd like to just make a side note about please visit those sites, especially the first one that Alberto shared. We posted all of the links in the chat. I think Brent did that. They're excellent resources, and I encourage all of you just to carve out some time in your week as you go along to explore how some of these tools can be used to get more equitable value, and then share with us what you find. I'd love that. So yes, thank you so much for attending. Our next meeting will be on March 19th at noon, and it will be more of a discussion around some of the tools that Alberto talked about today, as well as best practices for preparing your data and using them towards property valuation. And that will be taking place at the World Bank Land and Poverty Conference. If you're attending, please stay tuned for where we'll be advertising that meeting being held. All right, Brent, did you have anything you'd like to add?
No, I think this was great. It's a really nice introduction. And if you have friends interested in valuation using spatial statistics, I pasted the meetup link in the chat window as well. And we'll be digging down into details on each one of these areas that Alberto presented today and how it deals with valuation. But thanks everybody for your time, and enjoy the weekend. And we will get a recording out on this as well that you're welcome to share around as well. Thanks, Alberto. Thanks, Catherine.
Thank you.
Thank you.